degrees of trouble ends up being. All right, so no matter how you're getting there, you're starting, if we look at the rib structure first, we're starting with a surface. And we can take that surface and divide it, like I'm doing here. And I'm dividing into strips going in both directions. It's kind of useless in a way, now that I'm looking at this, that I'm doing this, because in the end, all I really needed to do was to get two edges of that surface, and I wanted to then be able to take those two edges and divide those up into points. And then taking and using those points to establish planes. My planes are very tiny. Taking planes, intersecting those with the surface to then get these curves. By intersecting those planes, I know these curves that I have are going to be planar. If I get curves that are not planar, nothing is really going to work very well in this definition. Yeah.
So quick question, because, well, in your example, the surface that you're working with starts off as a square grid.
Right.
So they're going to be planar
Right.
anyway.
Yep.
I started out with a non-square grid.
Right.
So I knew that each isocurve was going to curve as well in that dimension. If you were going to use this method and divide it by planar planes, couldn't you have also used contour?
Yeah, you could do that as well. The one difficulty with the contour is you take and you specify a distance between contours, and if your overall surface doesn't work with that module, then you could end up with a rib really close to the edge or one further away than you wanted. So this is just a way of making sure we get a rib at those ends, and then the ones in between. So a lot of times, if I'm trying to think how I can just take and generate a surface that's going to be crazy like that. Let me take for a second, take this. All right, I'm just trying to mess this up. So if I took, as I'm doing in my definition right now, and I extracted the edges of this surface and tried to then build my intersection planes off of that, I could end up with a mess because of how these isocurves get pinched at that point. So in that case, you would likely want to come up with a process where you either find the bounding box for this surface, and then you figure out, okay, that bounding box is this long, or you get an edge of that bounding box and you divide that edge up. Or you just create your own arbitrary line or frame around it. You could also take and say, come up here and draw a rectangle, and then use that rectangle in Grasshopper and use the edges from that to generate your planes. But in the end, you want to get a series of planes that are going to be, in this case, because this is mostly oriented in the XY axis, intersecting vertical planes with this will allow us to take slices through it, and we can then use those. But let's say I wanted to use that rectangle I drew instead of what I have developed right here. So I'm going to take that rectangle, I'm going to bring it into Grasshopper. I only want two of the edges of the rectangle, so I'm going to take and explode it. And then I need to use my list item to pick the 0 edge and the 1 edge. Remember, at any point, if I do something and it's confusing, stop me and ask a question. All right, so all I've done now is I've taken that rectangle, exploded it, and I have the two edges that are still showing up here in red. So I'm just going to hide that so we don't see it anymore, and I'll hide this for a second. So I've got these two edges. I could then take and divide those up, and I could just do a perpendicular frame here, because the rotation of our plane doesn't really matter as long as it's going to be vertically oriented. Well, that's only going to give me it at one point. So under division, perpendicular frames. So there we get planes going along the one edge.
So what exactly is a frame?
A frame is a plane, but a frame has been derived from either a curve or a surface.
So
In terms of using them, there's no difference. He's just making the distinction here to say that when you generate a frame, it's been derived from some other piece of geometry. Whereas when you create a plane, you're specifying an origin, an x vector, and a y, or an x-axis and a y-axis. A frame still has all those things, but it's just a way of making things a little more confusing for you. There's no difference between the two of them.
okay.
Just the way in which they're made. You do the same things with them.
It's a lot easier to get a frame if you already have. I mean, you don't have to figure out like what the cross product is or like orient it, which is kind of a pain.
It's easy to get a frame, but only if you're looking for a horizontal frame or a perpendicular frame. Those are the only two that you have the option of getting with it.
So in this case, because the curve you're deriving the frame from already has a perpendicular vector, the frame generator will be perpendicular to that.
Right.
No matter
So what the perpendicular frame does is we're specifying here saying that we want 10 segments to be divided up. And so at every one of those division points, it's just measuring what the tangent vector of the curve is, and then creating a plane at that point from that tangent, and using that tangent as the normal for the plane. So if we get a curve that's going around, if I have a crazy curve, and I plug that curve into here, the planes are then going to rotate around the curve. We don't need that right now.
So in this exercise, if your surface doesn't have orthogonal edges,
Right.
you end up with intersections that are 90 degrees.
If you use the perpendicular frames.
Oh,
If
right.
you follow the same process that I was going through, and in the end you end up using an XZ and a YZ plane,
Right.
those two
Then
are
you're-
always going to remain perpendicular
then you're good
to
to
each
go.
other, so you don't have to worry about it. Earlier in the quarter, Jeff had posted a video on the Catalyst discussion board where it was creating a rib structure, but it was a video showing the rib structure and being generated over and over as the orientation of the ribs was being rotated. So you can imagine creating two planes that are perpendicular to each other, rotating them both sets by the same amount at all times, and you could just take this entire thing and rotate it. And we can do that in a second with our rectangle that we drew. So I've got these perpendicular planes, and then I want to intersect it with something. And so let me get my one surface. I can't make that here. So I tend to, when I'm using Rhino and Grasshopper, just for sake of speed, if I don't want to take things and put them on layers, I use the hide swap to just quickly move back and forth between two views of the viewport. So when you hide something, it's not like it's just disappearing and it's gone from the model. Think of it as being put kind of into another world, and that's your hide swap world. And so if you take and type in the command hide swap, it's switching between the hidden and the visible. So right now, I'm in the visible, where all these layers are turned on, and then if I do hide swap, I'm going into the spot where I have some geometry that's been hidden from me. So it can be a convenient way of not having to take and flip things on layers on and off and just hide one piece at a time. It's also a good way of making a mess of your model if you don't keep track of when you're hiding things and then bringing them back to the visible side. Turning on layers on and off on this hide swap still works. So now that I've done that, when I switch over to here and I turn this back on, it now shows up on this side, so it can get kind of confusing. All right, anyways, so we've got a surface, we've got some planes. Now I'm going to intersect these planes with that surface. So go to the intersect. We're going to intersect a B-rep and a plane. So I've got my B-rep, got my plane, my frame, and I get those lines. Now here, because I did this as that rectangle, I'm not going to get lines all the way out to the edge. It's just going to go out to the extent of my rectangle. I can then copy this and use the other set of planes to get my pieces going in the other direction. Let me switch back over here, grab my rectangle. I hide that, and then I hide swap, and now I have it back on this side.
Use the SUC this side.
So now if I take this rectangle and I rotate it,
Plane intersection.
my intersections are going to rotate with that. So I could take and build up this definition off of these curves and get all of my notches and everything working, and then just come back later and put this rectangle at any orientation that I wanted, and I'm going to then get the rib structure generated at that orientation. You can also take and come up with ways where you're taking and maybe finding the bounding rectangle of this entire geometry given a specific orientation. All right, so that's just another way of getting to this point right here where we have those intersection curves. Okay. All right, so the next thing that I was doing within this was taking those ribs, intersecting them with each other. And once we have this, these rib surfaces are going to be what we intersect with the planes again in order to get those intersection points. Now we could take, there are components which will allow us to intersect a B-rep with a B-rep. But those operations aren't going to be as reliable, yes, as taking and getting more into intersecting a plane with a B-rep is mathematical intersection. So these will almost always work correctly. When you get into the physical, things can become strange because now it's looking at the geometry and trying to find the spots where they hit. So now you can get into issues with the tolerance of the model, how that is set up, as well as the definition of those individual pieces. And things might look right, but you could end up having a slight bend in how the surface was generated, and it'll just throw everything off.
Is that another reason then why Chad was mentioning the isocurve component? Because you could kind of get to this point by extruding isocurves.
Right.
Is that
As long as those isocurves you know are going to be planar.
Okay.
Because otherwise you could still probably generate a rib structure definition for that, but now all of your notches are going to need to be created in unique ways. But yeah, if you know that the surface is built off an underlying grid, then you could just take and extract edges out of that surface and use them to extrude that up and get to this point. Lots of ways to getting to the same place. So we're then taking with one set of these ribs and intersecting the planes that run perpendicular to that. So you've got these planes, they extend infinitely, so whenever you intersect them with something, they're just going to keep going and going. So we get all these lines. Now, as far as taking, and you had your points, and you were trying to use those points to now get these spots. And you could probably do that in the end, but if the points that you have coming into here, if the number back here going into that N input doesn't match up with what's happening down here as we divide this range up, then the two aren't going to match with each other.
I matched them up because I had different numbers in there, and it still didn't divide it the way the move divides. The move will just move the points of the grid up,
Right.
whereas the divide will divide the curve equally
Mhm.
in that direction, and it will always have a lag.
Right, right, because you took and you had these points originally, they're evenly spaced
Yeah.
down, but now if you draw this curve that goes like this,
Yeah,
they're
it's-
not necessarily going to line up in the exact same spot. So even though it might seem redundant to at times recreate data that you already think you have somewhere else in the definition, it can often be useful just because if you're working at a particular point in your definition, you want to take and make sure all the data is organized similarly. Want to make sure you can keep track of all of it. And you also don't want to spend all day going like this, zoom in and out all the way across your definition. So it can be helpful to just take and regenerate something, start from scratch at points. So we intersect those planes, we get these points or these lines, and then we find the midway point, and a rectangle is being created from that. Now the plane of that rectangle, I'm just taking in a way a shortcut here. I'm just specifying that's going to be an XZ plane. This makes it so that if my surface ends up being generated in a different way the next time, and the U and the V directions are flipped, all of this could break and not work. But at times, if you know, I knew I was only going to do this with 4-sided surface. I didn't have any other use for it. So I just was hard coding in, it's going to be an XZ plane. If you think it might change, then you need to find a way of deriving that plane from the geometry of your grid. So the plane is one part of it. It tells us where the rectangle is going to be drawn, but then the domain is the other portion for the X and the Y that's important here. Now this one that's being plugged into our X, that we're taking and specifying the material thickness and then saying go half the material thickness in the negative direction, and then here there's an expression saying go half the material thickness in the positive direction. So if we go half and half, now we have the full distance, and we've made sure that we're centering that rectangle on the plane that we're using here. And then for the Y domain, I'm just taking the depth of the rib and making the rectangle that tall. It's going to be bigger than we need it to be, but at least we know for sure that it's going to extend off. We could have taken and put a slider here and adjusted it so it was a little bigger than the rib, but then every time you change the depth of those ribs, you'd have to update the other thing. So in this case, I'm using the rib depth to then control the rectangle so that they will always increase with each other. So I should be able to then take and change, I forgot everything else is on, change my material thickness and have my notches get bigger. So this was a point where I saw a number of difficulties in people's definition, this region difference component. And the reason a lot of the problems seemed to be occurring was the path structures of the data coming into your A input and your B input. Now if I just take and I go directly from, I need to shut some stuff off, otherwise I could get myself in a problem. All right. So if I just took and went directly from my rectangle into the B, let me take and get back here. This is all I get. And I know that some of you had this problem, and I'm seeing the definition. And so when you have something like this happen where you're expecting something drastically different than that, you should have had a rib at every single one of those spots, and now you only have a bunch at the end, and I can tell there's a bunch because it gives me this weird rendering effect there. So there's a lot of them there. I can also hover over this planar input and see, well, I've got 99 planar surfaces being generated, but I can really only see 2. What's happening here is if we hover over the A input of the region difference, this data is coming in, and these are our ribs. And each rib right now is being held on its own path. And that's good. We can keep them all separate. That way any operation we perform on any rib that data is not going to get mixed up with another rib. You don't have to worry about sorting anything. So each one of these numbers right here represents one of we have 9 ribs total. Here are the numbers for each of those ribs. And then the n equals just tells us what we already knew. We only have 1 rib on each one of those paths. If I go down to this B input, here I have, and Jordan was asking a question about this earlier, how do you read this? How do you make sense of what this is actually telling you? Look at the top, look at the next few down to see how it's counting, and then look at the very bottom. So we see in this first branch on the left, it's all zeros right here. But in the second branch, it's telling us that it's got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this first 0 represents the 0 rib. And then every one of these numbers in the second branch represents the intersection of each plane with that rib. So we intersected 9 planes with that rib. So we get all these zeros and then the 9. Let me take and bring up another component and I can show you then what all the other paths look like. So under params, special, you've got this tree, param viewer.
That's the one with the.
Okay.
And this one is going to allow you to take and look at the data. If you double click on it, it's going to give you the crazy graphic. We're going to look at it this way. So you can see this is starting and it's the I don't want that one. That one's screwed up. I'm going to take the output of my rectangle component and just look what the path structure was for that. So the A input that we have here, that only has those 9 branches, 0 through 8. And now over here, this is that rib. That's the path structure for the rib. But then there's another branch being created because when we took that rib and we intersected 11 planes with it, it held the intersection for every one of those planes in a separate branch. And so that's what that second branch is now doing. This was the first intersection with the 0 rib. This was the second intersection with the 0 rib. Third, fourth, fifth, sixth, all the way to the 11th intersection with the 0 rib. And then it moves on.
So that's one rib.
That's one rib. All through here is one rib
Okay.
and all of the planes being intersected with it. And each intersection is being held separate and producing one intersection event. It runs out of planes and so it moves on to the second rib, rib number 1. This is the first intersection, second, third, fourth, all the way through. Gets the 11th intersection. It now has run out of planes again, so it moves on to the third rib. And it's going to keep going through this process. And each time it's taking and organizing the data so that you can look at all those intersections separately. And that was great while it was happening because that made it so that we could do individual operations on each intersection at a time. But when we get to this point here where we're trying to do that region difference, now we're trying to take all of those rectangles that we have, all these rectangles here, which are organized, if I just count through them, oh, wrong one. So what we want is we want the rectangles to be organized in this way, where we have all of them in one big list together. And I can see that they're in one list together because it's counting through them, 0, 1, 2, 3, 4, 5, 6, 7, 8. But it's holding the ones on this rib separate from these because when it starts counting these, it's also starting at 1 again. So we know at this point we would have the data organized according to each individual rib just by looking at how it counts through the items. Whereas if I take the output directly from this rectangle component, when we had those 2 different branches being created, and if I count these items, damn it, I did it again. So if I count these items, I get all zeros because every one of those items is on its own branch. That branch exists within the branch of the rib, but when we then take and use these rectangles organized in this way, Grasshopper can't figure out which rib those things belong to because it doesn't have the same address to look at for the 2 of them. So let me delete some of this clutter I just created here and look at what this is doing. This is the key to getting the region difference to work, this path shift component. So that's taking data that's coming in, has 2 branches. For now, we could not even worry about how many different levels within that first branch and within the second branch there are. Just as 2 branches. And when we use this path shift component, we're taking and specifying here how how and in which direction we want to shift that path structure. So if we put a -1 here, it's going to take any branches on the right-hand side and it's going to step to the left. If we put a +1 here, it'd start on the left and it would step to the right and remove a branch. So the data that is now going to come out of this D input or output is different than what we had coming into the D here. So let's look at those two in comparison.
So that took you from the zeros to the 1 through 10 or 11?
It took me from the organization of the first one being ribs and then each individual rectangle. That's how the data was organized before the path shift. Pull this up here, a little clearer. And after we shift the path, now we've removed that second branch, which was holding all of our intersections or our rectangles separate from each other. So now we're back to just the 0 through 8.
If you click on the graphic version of that, you basically just eliminated one
Right,
level.
right. Whereas if I look at this one, it takes and it starts, and I've got those 8 rib or 9 ribs right here. But then within each of those 9 ribs, I have 11 intersection events.
Okay.
So in a way, this is like flattening it just one layer instead
Exactly.
of flattening it all.
Yeah, we're hacking it off right here. We're getting rid of this stuff and putting all of those notches back into one list together. And now that one list for each rib has all the intersections for that rib together, rather than holding them separate from each other, which is initially what was happening in that rectangle component. So the data coming into your region difference right here needs to look like this. The path structure coming into A right now is just one path, 0 through 8 are my path names. And then in B, again, 0 through 8. Since those match up, Grasshopper can just take and say, the one that's a 0, match it up with the other one that's a 0. The one that's a 1, match those up, all the way through until it gets to 8. Before that, what happens is it takes and it looks at this path structure, which is just 0 through 8, and it looks at the other one, which has 0, 0, 0, 1, 0, 2, 0, 3, and it can only find 2 matches within that entire thing. So we get that weird, it tries to force it to happen, and it ends up giving us a mess down here at the end where it takes every one of the rectangles and tries to subtract it from that last rib, creating lots of copies of it. So the path structures get confusing here, but at the same time, they're what is allowing us to perform this operation on every one of these ribs at the same time.
So did you just align the rectangles using the sections? You didn't have to find the intersection points for the ribs to
I
use
took-
the rectangle?
I found the intersection of the plane with the rib, and that gave me that line. I then found the midpoint of the line. I created a plane at that midpoint, and then I drew a rectangle on that plane and had the plane go split the width on the point and then go in the negative depth, and then the other one I go in the positive direction.
I understand what clean did for you, but what did you prune?
So what the prune does is, at times, you're going to take and possibly generate, in this case, I'm probably not generating any. Yeah, it looks like I have the same number of data items, 99 to start, 99 after. But the prune will take any branch that you have within your data that doesn't contain any items, and it'll throw that away. You can also specify any branch that has less than 3 items, throw those away. So it's just a way of removing some paths. Simplify is completely different, because what Simplify is going to do is it's going to look at all of your paths at the same time, at all of their names, and figure out what all of them share in common. So if we added one more branch to all of this, which was a 0 out here, and that 0 occurred before every single one of those, they would all have that in common. So then when we do the Simplify operation on it, it would just throw that branch away because it's not really doing anything for us.
I tried to use like a physical intersection once, and it got me so much like junk
Yeah,
and like weird path structures that I was trying to use clean and prune to get it back to
yeah,
what it should be.
yeah. It won't clean up a lot of junk if there's actually junk there. This is just cleaning out, the clean component here removes any null values that you might have, empties, and then the prune removes any empty branches that you might have to keep your data cleaner. So I'll take, and I'm not going to go through everything that's happening within these tags right now. If you really want me to explain something, I'll explain it individually to people. But within here, using a set of operations to take and not only create the tag in the XY plane, but also back here, create a tag on the rib so that as I'm assembling this, if it was a little more complicated, I would be able to tell, okay, rib 1 is there, and then when I have my rib 1 over here, I can find out where it belongs in the overall assembly. But naming ends up being crucial when you're doing these types of things because it might seem easy that you're just going to pick it up at the laser cutter and stack it in the correct order and you're going to get home and everything's going to go together right, but it rarely ever works that way. You drop one piece or two pieces on the floor and then you forget which one was which. Hopefully you figure it out just by looking at them.
So how did you
Touch it
find
by
the
hand,
midpoint?
yeah.
Which is that component
I
that
like
you use?
This one. So this component here is a kind of like a curved slider. It's a point on curve, and it's doing a reparameterized value of that curve, or the normalized value. So when I put in 0.5 here, it's just going to give me the midpoint.
So you could change that basically if you wanted it to be a little beyond midpoint, maybe it's like 0.65.
Right.
Basically.
And the thing would be, in order for our notches to then work out correctly, we would have to do 1 minus that value down here. Because right now, if I do 1 minus this down here, it's 0.5, so it stays the same. But if I adjust this to some other value, and then I look at my notches, now they're going to pass by each other, and now you're not going to get a tight fit when you put this together. So I would need to make sure that whatever I have set up here, this one would become 1 minus that value to get those to end up at the same spot.
Where would you set that expression in that slider?
You don't. There's
Oh,
no way of
you
setting
have to
it in
do
here.
it.
You can get this same thing happening by using this component if you wanted to be able to set a value with the slider or some other number. So the evaluate curve, and then you would make sure to reparameterize it. All right, I'm going to jump down here. This doesn't prohibit you from asking questions later, but I just want to